Well, hello and welcome to Digital++. Episode 5 is finally ready and it has been a roller coaster. I had the code and the video footage ready and then had to insert a major release upgrade and redo everything from scratch. In this episode 5, we will upgrade our pink little avatar friend to a fully rigged FBX model. There's a lot of work which you may not expect at a first glance, and so the R&D slides will be quite extensive. If you don't want to know all those background and the details, you can jump right into the build sections in the video timeline, which I created for your convenience. Enough said, let's roll up our sleeves and get into the weeds. And there's a lot of weeds this time. So we want to move away from our small pink fellow here on the left side to a more advanced avatar on the right side. Unfortunately, there's a little bit more than meets the eye, and I'll try to explain in the next couple of slides. So first of all, our avatar has a monolithic skin and it's made out of a mesh. So moving hands, arms, legs, and the head means that we need to deform the mesh structure without wrinkling it. And we do that with what we call a bone structure. And that's something we did not have with our avatar that we created in part 1 and 2. Skin mesh and together with the bones is what we call a rigged model. Now there's an industry standard for that, and that's called FBX, and there are more standards like Wavefront OBJ and others, but we'll use FBX in this tutorial. And the good thing is you can download these fully rigged models from sites like Mixamo, but you can also generate or edit one yourself. So let's first open this model that we see here in Blender and see what that looks like. So I've opened the FBX file in Blender, and then we could go to object mode and we'll select the skin. Now we can go into edit mode, and then you'll see that the skin consists of a large number of small dots, what we call vertices. Vertices are connected into edges, and edges are connected into faces or surfaces. And you can start changing and editing those and updating those. As you can see, there are a tremendous amount of vertices in this model. Other than the mesh, there's something else that defines this object. So let's turn off the mesh and see what that looks like. So now you see that the avatar also has a bone structure, and these bones are very similar to a human bone structure. They're all related to each other. They start somewhere at the spine, and then you have a left leg, a right leg, left arm, right arm, neck, and the head, etc. All of these bones help with deforming the mesh. I will come back to that in one of the next slides. We've seen that a 3D model consists of a bone structure and the mesh consists of vertices. Two dots are connected by an edge, and then edges are connected into faces or surfaces. And so if you have 3 vertices, you have a triangle. If you have 4 vertices, you have a quad. The big advantage of a triangle is that it's always convex. That means that it's flat. And why is that important? So a face had 2 sides, and it has a normal. And a normal is a vector that is perpendicular to the surface. And that vector is being used to calculate light reflections onto the surface. So these normals are very important for the calculation. So you see here the sun is shining its light on the surface, and the light comes in at an angle to the normal and leaves the surface with the same angle as it comes into the normal, and then it comes into your eyes. So the GPU calculates the color and the intensity of each pixel on the screen, and then those calculations are done by shaders, and shaders are small C-ish bits of code that run directly on your GPU card. And there can be many types of shaders. And on a very low level, these shaders run in what we call an OpenGL library. The current library version is 4.6. Shaders run in parallel on the GPU core. So your GPU has a lot of cores, many more than your CPU has. And each of those can run these shaders in parallel. But you have to understand there's a lot of floating point calculations done by the shaders. And it's because the color and the intensity of each pixel on the screen needs to be calculated in real time. So now let's take a little bit of a sidestep. So what have GPUs to do with machine learning and AI? So let's look at AI at a 100,000 feet level. So on the top left, we see a very basic artificial neural network structure, and it's built out of nodes, and these nodes are called perceptrons, and perceptrons are in essence nothing more than a digital version of a human brain cell. So there's a lot of inputs here. All these come together, they're being summed up, and then there's a nonlinear function that's creating an output value. And so that's a node, and all of these nodes are now connected. So all this data flows from the left to the right in the perceptron, and that data flows is defined by what we call tensors. And tensors are in essence matrices with a lot of floating point values. And that's why neural networks heavily use floating point operations. Fortunately or unfortunately, the GPU also has what we call compute shaders. And those are shaders that do not bother doing any pixel work on the screen. They're just doing calculations, floating point calculations. So GPUs are very suitable for machine learning calculations, and they're much, much faster than normal CPUs. So you could wonder, why do we abuse GPUs for machine learning? Well, you're right. And what we see more and more nowadays is computers that have dedicated machine learning hardware, and they're TPUs, tensor processing units. So let's look at a 3D avatar. There's bones, right? And these bones are ordered in a hierarchy, and they start with the spine, and then they have a tree structure. So that means if you move the spine, the whole bone structure moves and your whole avatar moves. The bones movements are now defined relative to their parent bones. And that's what's called forward kinematics. So all of these movements and rotations are defined in relationship to each other. Now, unfortunately, the FBX structure does not prescribe how the bone names needs to be. So Unity has introduced what we call a humanoid bone mapping model. So we will come back to that when we go into the build phase, where in Unity you need to define how the FBX model is mapped to the human bone structure. Now, animations are predefined bone movement definitions, and all of these animations are based on forward kinematics. You can download animations. Now, virtual reality requires us to control hands and the head. That's going to break the forward kinematic rules. So inverse kinematics is available in the animation rigging package in Unity, and that will fix that problem. So a little bit of design work before we jump into the details. For the time being, we'll turn off the audio by default. If we do a lot of testing with our avatar, we don't want to constantly burden the Vivox network. At this time, each participant in our mini metaverse will have the same avatar. How to change that and make sure that every avatar looks unique? We'll look into that in future videos, where we will also apply machine learning to help us with that task. Our XR system only is able to track hands and head movement. So we need to find a solution for the leg. We will animate the leg movement of our avatar, and those will be controlled by the left and right controller joysticks on your controllers. Now that has an implication. That means that in the controller mode only you can walk around. In hand mode we will add capability to move your fingers. As we control the avatar with our XR origin, initially we will not add any physics components to the avatar. The position and scale of the XR origin will be auto-aligned to the avatar. And I'll have a slide on that in a second. We'll introduce a first and a third person view toggle in the UI. The solution that we have here is far from ideal. That needs to be fixed at a later stage. We want to retain the old avatar, so we'll create a new script. We'll make sure that the movement of all of our heads and hands, but also our finger positions, will be synchronized over the network using Netcode for GameObjects. So which steps are we going to take in our build process? So we'll start with installing the animation package. We'll do some cleaning up of our code, and we will turn off the Vivox audio service by default. Then we'll go to Mixamo, which is this website, and where we will download, install, and configure an FBX model that we'll use for this demo purpose here. We'll configure then the inverse kinematics for the hands and arms. Then we will configure the leg animation. So we'll download a number of animations for moving the legs. We'll install those and configure an animator. We will do a small update on the UI. We'll add a third-person toggle switch so that we can switch the view and look at our own avatar from behind. Then we will dive into our network player script. We'll create a new script called Humanoid Network Player, which is in essence the same as the old network player that we had in part 1 and 2. And we'll update that. We will then add controller for the animations in there. And then last but not least, we will make sure that all of these animations are configured for netcode so that we can also run all of this code over the network. In the next episode, we will look at inverse kinematics finger movements with netcode, but it's too much for this episode. That would be too long. So that'll be part 6. Okay, first of all, let's turn off the Vivox voice manager by default because we don't want to burden the network. We go to canvas and we go to the toggle, and then there's a checkbox here. Make sure that is on is switched off by default. So that was very easy. If you haven't done so, go to the scripts folder in your assets and make sure that all your scripts that you defined under assets are now moved under the scripts folder. So I already moved them in there, but if you haven't done so, it's just a bit of housekeeping. And then what you can also do within the XR origin, you have the left controller, left hand, right hand. And for some reason, this prefab just was not fully complete, and you get a number of warnings here because of scripts missing. Let's go to the 3 bullets and remove this script. The same for the right controller, so remove this script as well. Move component. Left hand, there we have a few. So let's remove that component. And there's another one that is missing. So that is also removed now. And let's remove these 2 scripts as well. 1 and 2. So those are gone, and that's already saves us with a bunch of annoying messages. Now we go to mixamo.com because we want to start downloading our avatar. So mixamo.com. I already signed in. And then you have characters and animations. So let's move to characters. And you see the guy that we want to use already. But you can download whatever which one you want to try out. You even can download it from another place. But Mixamo is usually a good place to start because the avatars are really complete. And the guy that we want to have is called Josh, and he is on the 2nd page. So let's do download. We want to have the FBX for Unity in the T-pose. And there we go, we download that. So let's go into our downloads folder, and we have a file called ch23 non-pbr.fbx. Move that into our prefabs folder. And then we don't move it into the scene yet, we just click on it. And then we go to the materials tab, and in the location field, use external materials legacy. Apply, ignore any warnings. In the rig tab, under animation time, please select humanoid, because that is the mapping of the bone structure to the humanoid bone structure, and apply. Now what you can do is you click the configure button, and now you can see that everything is green. So if something is red here, Unity was not able to map the bone structure of the FBX to the humanoid bone structure. So let's go back, click on the small arrow here on the top left side where my pointer is now. So let's go into scene view and now drag drop this into the scene. The first thing we want to do is go to Windows, Package Manager, and with Unity Registry selected, we will type animate. And then we'll import the animation rigging. So let's install that. Right, so that's now installed. No need to install the samples, so we'll close it. We'll select the avatar here. We'll change the position into 0, 0, 2. And the rotation should be 0, 180, 0. You'll see that after the installation, we have a new tab in the top menu, which is called Animation Rigging. With the avatar selected, we'll go to animation rigging and we'll select bone renderer setup. So this will show the bone structure of the avatar, very similar to what we've seen before in Blender, if you recall. Default color is a bit ugly, so let's make that a bit whiter. Now we have the avatar here, and what we'll do is we'll create a new game object and we call it XRIK rig. And we'll make sure this has position 0, 0, 0 and rotation, and we'll add a component here, rig. You get a warning here, ignore that, we're going to fix that now. In the humanoid avatar, we add a component rig builder. Let's drag the XRIK rig into the rig layers field. There you go. And let's now start building out this game object. So we'll add 3 objects. The first we'll start with right arm IK. Be very careful with your names. We'll add a 2-bone IK constraint. Create a new game object. We'll call it left arm IK. It also has a 2-bone IK constraint. And then we'll add one for the head. So we have then the left arm, right arm, and the head. The head requires, it has a multi-parent constraint. Okay. So let's start with the right arm IK. We'll open the bone structure, which starts here at the mixamoric hips, spine 1, spine 2. Again, if you selected another model, the names could be a bit different, so you need to figure that out. We go to the right shoulder, we go to the right arm, to the right forearm, and to the right hand. So let's click the right arm IK. We drag drop the mixamoric right hand onto the tip of the 2-bone IK constraint. And now we click the 3 dots here and we do auto setup from tip transform. So it now has automatically found all the objects related to that. And what it also has done, it has created an IK target and an IK hint. So let's click on the right hand IK target first, then press Ctrl and then click the right hand in that order. Go to animation rigging and click align position. So now your right arm IK target is positioned at your right hand. All right, we'll do the same for the left arm IK. So let's select the left arm, left forearm, left hand. Pick the left arm IK. We move the mixamoric left hand into the tip of the 2-bone IK constraint. 3 dots. Auto setup from tip transform, and then open up the newly created objects. Select the left arm IK target first, then with the control key pressed, click the mixamoric left hand, and then we go to animation rigging align position. So those are now aligned. And then last but not least, the head IK. Let's click, close those, then we go to the neck. Here we see the metamorphic head. Let's go to head IK. The constraint object is the head. So let's move the head object into the constraint object. Now we need to have a source object field. So let's click the plus to create one, and now create manually a new child object for head IK. We call that head IK underscore target with small letters. Let's use the same naming convention as the ones that were automatically created for the left and the right hand. And the head IK target we move under the source objects. So that should now be done. Then last but not least, we need to configure 2 more things. So you see there were created a right arm IK hint. We go to the transform here and now we click reset. And the same for the left arm IK hint. Those are now reset to 0, 0, 0. Basically what these IK hints do is they are the direction where the elbow will move to as natural possible way. Let's set that for position at, apologies, 0.5 and minus 0.5, minus 0.5, so that the elbow goes downwards and behind the avatar. And for the right arm IK target, which is 0.5. minus 0.5, minus 0.5. There you go. Great, so that's now completed. We will drag drop the avatar into the prefabs folder again, and we'll rename it Humanoid avatar. And now we can delete this from our scene. With that, we have our avatar configuration completed. We've now configured inverse kinematics for heads and arms, and we now need to create our animations for the legs. So the first thing we'll do, we go to Mixamo and download animations. We'll install those and then configure the animator. Let's open our browser and go to mixamo.com. Okay, so the first thing we want to do is have an idle animation. I think this is a nice one. So let's go to download. We do FBX for Unity and we want to do it without skin. So download that. Then the next we want to have a walk forward. This one is good. So let's do download FBX without skin. Then we want to have walking backwards. Well, I can take that. Let's download. Looks a bit aggressive, but we'll try it. Then we'll do strafe. So we'll only need to download one because the left and the right animations are the same. You can mirror them in the animator. So let's do a walking strafe. Let's download this. And the only other thing we now need to download is a turn. So do a left turn. Let's do this. This is funny. Good. So now we've downloaded this. And let's go back into Unity. Okay, so we're back in Unity and then let's import our animation. So the first thing we do is we create an animations folder. Let's do a create folder. I'll call those anim and we'll double click on that. And then we go to downloads. We select our idle, left strafe, left turn, walking backwards, and walking. Let's select all of them first and make sure that we go into the rig tab and select humanoid and then apply. So now all the animations are aligned to the humanoid skeleton. The things we want to do for each of those animations, check the name here in this field. So if it's a readable name, so this is idle, that's good. And make sure loop time is turned on, otherwise it will only run once. Okay, we'll do apply. And we have to do the same for all of these. Now walking, loop time, and then the last one, walking backwards. And we'll make sure that's also looped. There's the loop, here's the loop, apply, all done. So those are created. Now we do a right click, we create a new animation controller, and we'll call it leg animator. And let's double click on that so it opens the animation tab. The first thing we will do is we will create an idle state, and it will automatically create that there. Now let's go first to our base layer settings. Let's change those and turn on IK pass. That's crucial for a script, so we'll come back to that in a bit. Make sure we have that in there. In the parameters, we need to create a couple of parameters first. So we'll create first a boolean that is called is moving, so that decides whether or not we're going to move forward or backwards. And we'll create another one which is rotating. And now we create 4 floats for each of the forward, backward movement, and the left and the right rotation. So we will say direction X, and we do direction Y. We'll come back what that means in a second. Okay, so now we create a new blend tree for the rotation. So we'll call this rotation, and let's open that up. And now we make this one 1D, and we create 2 motion fields. The first motion field is a left turn, and the next one is also a left turn, but we'll make sure we do the mirroring there. So one direction is left, one direction is right. We don't want to automate the thresholds because I want to set them myself. So a -1 threshold is a left turn. If we do a +1, it'll be a right turn. Let's go back to the base layer. We'll create a transition from the idle state to a rotation state and make sure we turn off exit time. Please don't forget that, otherwise the transition will be limited to amount of time. And then we add a parameter and say if is rotating is true, then we'll move from idle to rotation. Okay, that's done. And now the back, so we transition back from rotation to idle, and we click that, turn off has exit time, and we say the condition, if rotating is false, you go back to the idle state. Finally, in the blend tree for rotation, let's make sure that the parameter for the rotation is rotation X. Now we create a new blend tree, and no surprise, we'll call that movement. Let's open that, and this will be, let's click on this. This will be a 2D simple directional one. And we'll have direction X and direction Y determining how that is moving. We will have 4 motion fields, 1, 2, 3, and 4. Motion 1 will be walking forwards. Motion 2 will be left strafe walking. Should be a mirrored one, so make sure the mirroring is on. So this is a right. Then the next one is a walking backwards, and then the last one is a strafe left. And now position X for walking forward will be 0 and the Y will be 1. So that means that if our left controller is in the upward position, the avatar will start walking forwards. The right is a -1 with a 0. Then the backwards is a 0 and the Y will be -1. And obviously the left strafe will be 0, 1, 0. So now we select this again. So direction X and direction Y now determines how the avatar is walking. Good, so let's go back. And then we create a new transition state from the idle state to move. We uncheck has exit time, and we create a condition where is moving is true. We'll move over to the movement, and now we go back from movement to idle and has no exit time, and we say if is moving is false, we will move back to the idle state. So now that is completed. So that now means that our animator is done. So we go into our prefab humanoid avatar, and then there's an animator field. So the thing what we do is on the controller field here, we can now select leg animator. So now our leg animator has been assigned to our prefab. Great, that step is done. So we've now completed the leg animation, and we now want to continue with a small update on the user interface to enable that for a third person toggle. So back in Unity, let's go to the canvas, And you see we have a toggle here. Please make sure your text field is a child of the toggle. I may in the previous parts had that as a separate object immediately under canvas, so you should drag drop it under toggle. So the great thing now is you can duplicate that and you'll move it a little bit down. We'll rename this to camera position and we will change the text here to third person. There we go. That was all. And obviously the implementation of that we will have to do in the Humanoid network player script. So UI update is done. And now we'll go into the hands and the head movement and the AutoTune. So let's roll up our sleeves, folks, because we're going into the weeds when it comes to our scripting. Let's quickly look at the program structure that we want to build for the Humanoid network player. It's very similar to the network player script. So on the left side, we have two functions called onNetworkSpawn and onAnimatorIK. Those will only run once. OnNetworkSpawn replaces the start function, and that's to make sure that we only launch the avatar when it's actually available on the network. And in that function, we want to create all the pointers to the XR origin. And then we also want to create the pointers to the avatar hands. In the update function, we can use those and we don't need to lose precious CPU cycles on that. The onAnimatorIK function is triggered by, if you remember, we created the animator. So let's go back to Unity. In the animator and the base layer, click the IK here and you see IK pass. You have turned this one on, the onAnimatorIK function will be called. And we will use that only once in our function to auto-tune the avatar. And why is that? We want to know the exact position of the foot of the avatar. In the update function, we do a quick check on first person 3D camera offset. And then we will check on the left hand and see what the local position is of the avatar's left hand. And we calculate that from a global XR origin position. And then for the left controller, we have two options. You move the left controller in the X direction, you will launch the strafe animations. If we move the left controller forward or backwards, we have the walk forward or walk backward animations. For the right hand, we will do the same thing. For the head, what we do is that we only check the rotation from the XR origin. We don't need the position. And that's because the new avatar that we have is a monolithic object with a bone structure. So there's no need for us to set the position of the head of the avatar. And finally, last but not least, the avatar body position and rotation will be set based on the position of the XR origin. So the really first thing I would like to do a little bit of just to be sure code. I just want to make sure that we initialize everything properly. And the reason why I'm doing that is that in some cases when you start the application in your standalone mode, so from your VR system, the XR origin is not properly starting in the right direction. So I'm going to add some code here, XR hands setup, and we add a component, a new script called init, and let's open that up. Start. So we want to have a link here to the XR object, which is this transform. And we also want to have a transform for the camera object. GameObject.find camera offset .transform. We want to have a transform for the main camera .transform. We want to have a vector 3 for the initial position in that pos, and that is a new vector 3 0 0 0. Hard force that to 0. And then I also want to have a quaternion, which I'll call init.rot. And that's a new quaternion.euler 0 0 0. And new not new quaternion, it's quaternion.euler. I need to remove that there, my bad. So xro.position is init pos xr rotation. Yep. We want to do the same for the camera object. So the camo.position init pos. And then the camo rotation is init.rot. And then last one, the main camera. There we go. And then we'll do a debug.log. Position XR origin, xro.position plus camera offset plus camo position plus main camera plus main c.position. And we'll do the same for rotation. So copy paste it and rotation. There we go. Again, this is for us to have an option when you are in standalone mode to see whether or not the XR rig has been properly initialized. So let's go back to Network Manager, Player Prefab. Now we want to move to our humanoid avatar. So Let's click there. There we go. So we now switched over. And then we go to our prefabs folder and then we open the humanoid avatar. So we want to add components and we do a new script and we call it humanoid network player. That's a new script. By the way, make sure we move the humanoid network player and the init script into our scripts folder. Place them over here. Now we go into our scripts folder and let's open up the humanoid network player. So we can remove the start functions because we don't need that. First thing we want to do is we want to copy as much as possible from our network player script because we want to reuse all of that obviously. We will copy paste all the class definitions. So we'll put those in here. It obviously doesn't know the XR input modality manager, so we will include the inputs. Yep, on network spawn. So let's make sure that that is available. So we'll create that ahead of the update function. We'll replace the update function with the one that we had in our manager. So let's replace that. And then we should have this in place. Let's see if we have any errors. The on network spawn. And one thing we need to fix here is obviously the human network player is a network behavior. And let's see, we have a toggle here because it doesn't know the user interface. So let's add that. So that is all fixed. All right, so that is done. And we now have the humanoid network player, which is basically a copy of that network player. First, we have to go back to the prefab. So let's add a few components just to make sure we don't forget those later. So we want to have a network object and we want to have a client network transform. And we don't want the scale to be replicated as before. And that is fine. And then the other thing we want to do with humanoid network is then for now we can turn off the bone render because we don't want the bones to be rendered. We need to align our XR origin to our avatar and not the other way. To do that, I wanted to implement a function called AutoTune, which will be run only once, and it'll look at the size of the avatar versus the size of the XR origin. So we will look at the height of the eye position of the avatar, and then we will also look at where the toes of the avatar are. To do that, we will need to have access to an animator IK call. So we'll use that to identify the position of the toe of the avatar. And the difference between the two is the height of the avatar. Now for the XR origin, the XR camera height is basically the height of the XR origin. You can very simply calculate the scale of the avatar, which I branded avatar scale as the avatar height divided by the XR camera height. Okay, so let's keep that in mind and then we start defining some variables in our script. So let's add a float avatar scale. I want to add a avatar height. I want to add a avatar toe Y position and an avatar eye Y position. So these are three variables that we need for AutoTune. I also need a bool because I want to make sure that our AutoTune runs only once, and we'll start that with false because it obviously has not been started yet. And we want to add a few serialized fields, and let's add those to the bottom here. Serialized fields, and I want to have a vector3 and we call it third person offset, and I also want to have a first person offset, and we'll define those in a bit. So that is now done, and then finally we want to add another variable called transform my camera offset. I want to use that for the third person toggle. Yep, and I want to have a toggle and we'll call that third person toggle. And now we go to on network spawn. Once my XR cam has been found, we will add another pointer to my camera offset, GameObject.find camera position. If you remember the avatar, we created a XR IK rig. Let's make sure in our script that we create the new pointers. So AV left, what we want to do is we change that to transform.find. We want to find the XR IK rig, and then we want to find the left arm IK, and within that we want to find left arm IK target. For the right, I'm going to copy paste this over and we'll change this to right and this to right as well. And for the head, we want to find the head IK, and this will be head IK underscore target. You can make easily mistakes here and then you get null pointer reference errors. So let's make sure you do that right. And the AV body is now just the transform. Then what we want to add is a third person toggle, third P toggle, GameObject.find camera position .get component toggle. So we now know whether or not this is on or off. And my camera offset, let's change it. So my camera offset is GameObject.find camera offset.transform. So that is the offset of the camera. Okay, and then in update, we need to make a few changes. We will define a new vector only locally in this function, vector3 camera position offset, and that is my camera offset dot rotation multiplied by, and now we have a compound statement where we say third P toggle is on. If it's on, then we want to use the third P offset, and otherwise we want to use the first person offset. We'll need to multiply that by the my camera offset rotation to make sure that the avatar rotates with you. What you want is that the avatar stays 100% directly straight ahead of you. And then, so we now need to update the positions of the hands and the head. But before we do that, we first need a slide. Let's quickly switch to that. So in our update function, we were just about to code the local hand position for the left and the right hand. So first of all, let's look at our left hand, and we'll do the same for the right hand. So on the right side here, you see our VR system with our controllers, and Unity takes care of all the code to create an XR rig with a camera offset and the left position of the controller. So if you look carefully, the XR rig is the main object. There's a camera offset underneath that, and then the left position of the controller is defined in relation to the position of the camera offset. So how do we transpose that onto our avatar? In tutorial 1 and 2, we had our old avatar, and there we said, well, the position of the left hand is exactly the same as the position of the left controller. Now, unfortunately, that is a bit more complicated in this size, because the position of the controllers is not necessarily using the same coordinate system as the avatar. So the best thing to do is take the difference of the camera offset and the left position of the controllers and then transpose that onto where the position of the left hand is of the avatar in relation to the position of the spine of the avatar. And that's what we do with the formula above there. So we don't use the left hand position, but we use the left hand local position. So with that, we define the position of the left hand in relationship to the spine, not to the global coordinates. But we basically say we take this vector here between the left position and the camera offset of the XR rig, and we transpose that onto the coordinate system of the avatar, and that's how you get this formula here. Back into our update function, so we'll change this formula here. Let's uncomment AV left position, and what we now want to do is AV left local position is a quaternion dot inverse the my camera offset dot rotation, and then we multiply that by the difference between the left controller position, and we subtract there the my camera offset dot position. All right, so that's for the left position. What we'll do there, we'll copy and paste this, we'll comment this one out, and we make the local position, and now you need the left hand position and not the left controller, obviously. For the right, we'll do the same, so we'll comment this one out, and we will just be lazy and change that. Right controller, and then we copy paste this again, and we uncomment this one. Let's keep it just to be sure. So, and this is for the right hands. Okay, that's completed. So just to be sure again, these are conversion statements where we convert the global position of the controllers and the hands from the XR origin to the local coordinate system of the avatar. And that causes a much more natural behavior instead of just using the raw global position. So for the head and the body, we'll do something very similar. So we'll, as I said, we will not need the AV head position anymore, and we can use the rotation. And the AV body position equal to the my XR rig transform position plus the camera P offset. So it's the position of the body is the same as the position of the XR rig, but obviously we want to have an offset here based on whether or not we selected the third person view or the first person view. And now we want to have the AV body rotation. That is the my XR rig transform rotation, and that should be it. And then a final note, please note that the camera P offset, which is the variable that defines whether or not we are in the first or the third person view, only needs to be applied to the avatar body, because we use for the left hand and the right hand the local position, and that is, as you remember, defined in relationship to the spine of the avatar, so we don't need to apply that to the hands and the head, which would have been the case if we would have used global coordinates. So now let's quickly look at Unity and let's configure the settings of the UI for this script. So let's go to prefabs, we click on our humanoid avatar, and then we go down to the humanoid network player script. The left rotation offset, we need to rotate our hands 19 degrees. The same for the right hand. The head rotation offset .001. So you need to make a very small amount, and that's because these three XYZ rotations are what we call Euler coordinates. And the risk with Euler coordinates is if you make them all 0, you would cause gimbal lock. So the third person offset, we will move the avatar 1.5 forwards, and in the first person offset we'll put it behind you a very tiny bit. So that should be enough. Let's cross check. We have our network object. We have our client network transform. The bone renderer is turned off. We have our rig builder and we have our animator. Great. Okay, so we're now ready to test. Let's go back to our Unity project and let's launch the project and see where we are. I'll turn on my headset. We'll just use it in USB mode, right? So we have the USB cable here. You see the voice service is now turned off by default. You do see my hands here and they look pretty big. So let's switch to third person mode and you can now see that the avatar is there and the hands are naturally moving the position of my real hands. And my head is tracking as well. I can switch to my hands instead of my controllers and you see that it also tracks it in the right way. Awesome. So now let's turn around and you see the avatar stays exactly in front of the camera, and that's also because of the fact that we multiplied the position by the rotation of the XR origin. Now the thing you do see is that the avatar is quite big, much bigger than we are, and so we need to do some sizing and tuning of the avatar. So let's go into that now. There's two things that need to be fixed. One, the avatar is much bigger than we are, and so the XR origin is not aligned to the size of the avatar. And then the next thing is that the legs are not moving yet. So the first thing we'll do is we'll start going all the way to the top of the class definition of the humanoid network player script, and we'll create a couple of additional variables. So we'll need a way to track the inputs of our controllers. We will have two variables of the type input action, a right turn action and a left move action. We'll need to fix that by using Unity engine.inputSystem. There you go. And we also want to control the animator there. So let's make a link to the animator object. So we call that AVT animator for animation control. So let's go to onNetworkSpawn. In the onNetworkSpawn function, we want to add a few lines to define the right turn action and the left move action. So right after the definition of the XR origin, we will create the right turn action. That is a GameObject.find turn. For that, we want to get the component action-based continuous turn provider, and it doesn't recognize that, so we need to have the interaction toolkit added, and we need to have the right hand turn action. The left move action, very similar, is a GameObject.find. It is the move.get component. Probably will not be a surprise what we're going to do. Action-based continuous move provider dot left hand move action dot action. So what we're basically doing is we're pulling the results of the left hand joystick and the right hand joystick into these variables. So that's done, and now we also defined an animator, so let's try to get that as well. The avatar animator is the transform.get component of the animator. Obviously this script that we're running here is a part of the avatar, and the animator is a component of the avatar, so we can use the transform.get component. And now AVT animator is a link to the animator component in our script. Next step up is we enabled the inverse kinematics in the animator. So with that, we can call a function called onAnimatorIK. So let's define that. Private void onAnimatorIK. So what we want to do there is, if you're not the owner, just as well return immediately. There's no need to do anything there if you're not the owner. If we don't have the avatar animator defined, then we can also just as well return. So now if you remember at the beginning, we defined a variable called AutoTune, and we had a slide for that. So if not AutoTune, because we want to run this only once, and by default AutoTune is false. So if AutoTune is false, it means we haven't run this function yet, so we'll need to run it only once. So now we go to the avatar eye position, AV head position.y. Okay, so let's go into our scene, and we have defined, if you remember, the XR IK rig and the head IK target that is pointing to the AV head variable. If you click that, you see that the Y position of the head is actually somewhere in the neck, and we want to have the eye position of the avatar. So the best thing to do is that we multiply this AV head value with about 10 to 15%, and therefore this brings us closer to the actual position of the eye of the avatar. So back in the script, avatar eye position, and then we multiply that by, let's say, 14%. So that is that part. Then we want to define the height of the avatar. So the avatar height is now, if you remember that slide that we had, the avatar eye position minus the avatar toe position. And then the avatar scale is defined as avatar height divided by the myXRCam position.y. However, you could run in a situation where you're running this application as a host and you don't have an XR rig connected to it, and this will cause all kind of nasty errors. So let's do an additional check here. So we will check if the myXRCam position.y, and if it's not 0, then we will just calculate that. If it is 0, something is wrong with the definition of the XR rig, and then we'll just return 1. What we'll do then is a debug.log XR origin scaled to avatar scale. AV left hands controls manager m_left input mode. That is XR input modality manager input mode motion controller. Then we want to return the my XRLC position. It's a logical controller. And if that's not the case, then we want to return the hand position. And then we do the same for the right. It's the right input mode, right controller, right hand. Right. So what we do here is we do an initial set of the global position of the avatar hands. Once we're done with that, we only want to run this function once, of course. So what we then do is we say AutoTune is true, and with that, in the next cycle, this will be ignored. So now in update, what we can do, well, we do know that if AutoTune has not been set yet, then we can also just as well return. So AutoTuning is complete. Yes, we forgot to scale, so now we want to add the myXRrig.transform.local scale is a vector 3. It's avatar scale, avatar scale, avatar scale, avatar scale. Good. Let's make sure we don't forget about that. Otherwise, we calculate the scale, but we don't actually execute on that. So after we've defined the position and the rotation of the left controller, let's make some space here. We now want to find a variable, left controller move value y. We want to check what is the value of the left controller, and that's the left move action read value. That's a vector 2. And from that vector 2, what we want to have is the second value, because the x is the first value, so that's number 0, and the y value, so that's the vertical position of your left controller, is the second value. If that left controller y value y is 0, then the avatar animator setBool is moving, false. So what we're saying here is that if your left controller joystick is not in the upward or in the downward position, then the avatar is not moving. Else, then the avatar animator.setBool is moving is true, because now we are moving. So actually now we start executing the animator. And what do we need to do? Well, we need to set a float value. We're now moving into direction Y, if you remember, the left controller value. So let's quickly switch back to Unity and see what we are doing. So in the animator, let's go to the movement blend tree. Let's look at position Y. If it's -1, we're walking backwards. If it's +1, we're walking forwards. We manually configured those. So what we said in our script here, if we're moving the left controller joystick, then we're literally passing on the -1 or the +1 value to the direction Y value of the animator. So we're directly moving the value of the controller to the animator. And that's how this piece works. What we now want to do is also add a piece of code here. So let's copy paste this code and just update it, because we also need to have the X value. The X value is the first part of the vector that you read from your joystick. And so if your left controller move value X is 0, then you also set the rule of is moving as false. Then if it's not 0, then we make it true again. And now we need to set direction X, and we'll do exactly the same here. We just use the X value. Now the hand, we don't need to define any animations for that, because we will not animate the legs if we're in hand mode. Later on in the next episode, we will add code here that does start the tracking of the finger movements, but for now, the tracked hand does not allow for any movements. Good, and now we go to the right input mode, and well, you can probably guess it'll be very similar. So, but now we have only one section. So I'm going to again, after this, I'm going to copy paste the same. But now what we do is we change that into the right controller turn action. Obviously it's not move action, right? Turn action read value. We create a right control rotate action X, rotate value X, I have to say. That is right turn action read value. Then the right controller rotate value X, if that's 0. Then we make sure we don't rotate, otherwise we turn on rotation in the animator. And how much rotation do we have in which direction? Well, the value of the right controller joystick will immediately pass that on. Not if rotation is rotating. Let's fix that as well. Okay, and before we can actually run and test this, we need to add 1 or 2 more things, which I forgot to type here. So we need to obviously also define the avatar toe position, and we want to get that from the AV animator, and we want to get the IK position. So now we are going to get the position of the foot. So AV IK goal dot left foot dot Y. So what we're doing here is we get the position of the foot from the IK system. So we're back in Unity, and let's turn on the headset. And let's turn on application, see. All right, so let's start as a host, and let's start a third person view. And you immediately see that the avatar is now auto-tuned its size. So it's equal height as myself. So I'm looking exactly at the eye level as the avatar. I can move forward. I can move backwards. I can strafe left and strafe right. And then, by the way, let's look, the origin of the XR has been scaled to factor 1.4, so the XR has been reduced by 1.4 size. I can turn. You can see that the avatar is making turn moves, and the other way around as well. So that also works awesome. Let's go quickly into the animator and see in our blend tree what is wrong with the movement. So you can open that here. And let's click on that so you can see it's moving. So now let's move the dot forward. So it's now moving nicely forward. I can move backward. It's now doing its backward walk. Awesome. And now let's go to the left. Yeah, it looks like the animation to the walking to the left is a bit weird. And to the right. So let's see what happens if I switch that. Let's do a mirror. Let's switch the mirror for left strafe, right strafe. So let's see. Yeah, this looks better. So I'm moving to the left. You see it now moves to the right. Yeah. Great. Let's do a final test just to be sure. And let's run this thing in standalone mode, see how that works out. So we go to File, Build Settings, and then we do a build and run. Okay, so that took about 8 minutes to compile. It's now standalone on the headset, and I'm running it on the host. And then I'll connect as a client, and we'll see. So we'll start here as a host. There we go. We'll switch to the scene. So here we have our host, which obviously has no XR controller, so it is in T-pose. And I'll join as a client. Let me turn around and look in Unity. So you do see now that the avatar is showing, but unfortunately it is not moving its hands, its head, or no animation. So let's try to fix that now. So the first thing we'll do is we want to enable the hands and the head for network movement. And the way we can do this is, the avatar is controlled by the IK targets. So let's select the left arm, the right arm, and the head IK target. We add a component and we call it client network transform. And then we remove the scale. So now the hands and the head movements should be replicated over the network. Now the second thing we need to do is we need to create a network animator. Now unfortunately, very similar to the way the client network transform is defined, the standard network transform is server authoritative, and we'll have the same problem with animation. So we'll need to create a new component. So let's go to the humanoid avatar prefab and we'll create a new script, client network animator. Create an add. So let's open the client network animator. And the thing I want to do there, we can remove start and the update function. And this one inherits from network animator. Include netcode components. And then we create a function called protected override bool on is server authoritative. That was automatically generated, and we don't want to return this based on server authoritative, but we just want to return false. That is done. The only thing we now need to do is drag drop the animator object into the animator field. And that's because this client network animator has inherited from network animator, and that has an animator field, so we need to make sure that it knows the animate. Let's see if we can build this, see if we can make the animation run over the network. This should be faster than the previous step. And let's now run the application. Start in host mode. Yeah, and I'll join from my VR headset, and I start as a client. There we go, let's move around. Yeah, so you now see that my hands are replicating over the network. My head movement is, so I'm turning my head, that is replicating. And I can move forward. You see the animations also replicated. Left strafe, right strafe, rotations. All of that working awesome. Okay, and this rolls up episode 5 of building a metaverse. So we've downloaded an FBX model and we got it to animate. And the only thing we now need to finish is detailed finger movements. That was too much for this episode. This one's already pretty lengthy. So please join me in episode 6, where we will finalize the finger movements of the avatar. Hope to see you soon, and thanks for watching. Bye bye.